In this section, we're going to introduce the Fourier transform, which derives from the Fourier series. Now, the Fourier series that we've been looking at is for periodic functions. So if you have a periodic function, you use the Fourier series. What we're going to do in this section is we're going to show, as we can see on the figure at the right, that if we have a non-periodic signal, such as this rectangular pulse that goes back to 0 for infinite time in either direction, that it can also be looked at as a periodic signal if I repeat that rectangular pulse multiple times in time. And so what we know how to do is, if I have a signal that repeats an infinite number of times, I know how to calculate the Fourier series. So as a first step to doing the Fourier transform for non-periodic functions, we are going to see how the Fourier series changes as I let the period of a fixed model signal increase without bound. And that will give us some insight to what is going to happen in the Fourier transform, and it will also be a useful exercise because the math that we use in deriving how the Fourier series changes as I increase the period but hold the signal constant, that math will be useful for us in the Fourier transform. So for a non-periodic function, we will use the Fourier transform. In this section, we derive and introduce the Fourier transform. A little bit later in the chapter, we're going to derive some useful properties. And then we'll see what happens if I have a periodic signal, which I would normally use the Fourier series on, and what if I apply the Fourier transform to it. And that can be done, and we'll see what happens in that case and how to handle it. So let's derive the Fourier series for the repeating rectangular pulse shown in cases A and B at right. So we have the Fourier series coefficient is equal to 1 divided by the period. The integral over a full period, let's do minus half the period to positive half the period of the function times e to the minus j, then it's the frequency and the time variable. The frequency is n omega naught, and the time variable is t. Now, we see that in case A and case B, as t naught, the period is increasing, the omega naught is also becoming a smaller and smaller number. So longer period leads us to a smaller frequency, omega naught. But we can let t naught and therefore omega naught be a variable, as we can see how it varies between case A and B at the right. And now we want to go ahead and do this integral. So we see that most places the rectangular pulse is at a 0 value. It's only on between minus tau halves and tau halves. So everywhere else, it's x of t is going to be 0, and we don't need to evaluate the integral. In that range, minus tau halves to tau halves, the value is just a, and we multiply that times the rest of the expression here, e to the minus j and omega naught t. And now we are integrating an exponential, so we have to divide by minus j n omega naught t naught, because that is the coefficient of the variable we're integrating with respect to. And we still have e to the minus j, frequency is n omega naught, time is t, and we evaluate that from t runs from minus tau over 2 to tau over 2. So now we substitute in the upper and the lower limit. So in the fraction out front here, I have a, and in the denominator, I have n omega naught t naught, and I'm going to take care of the rest of that in a minute. We'll come back to that. But let's substitute in the upper limit. So we replace t with tau over 2 at the upper limit. So, and we're going to write this as the numerator of a fraction. We'll see why in a second. So I have e to minus j n omega naught, and the t becomes tau over 2. And then at the lower limit, t is negative tau over 2. So when I multiply that out, the negative sign in the exponent goes away, and I have plus j n omega naught tau over 2. And that expression comes from Euler's formula's expression for the sine wave. And if I put that over 2j, then I have the expression for a sine. So the j I got from over here, and to get the 2, I am going to have to put a 2 here, and I have a negative sign left over, so I will leave the negative sign right there. So now that is the expression actually for negative sign of the argument. So we can simplify it a bit further. The negative goes away because its negative sign is that fraction on the right. And I have sine of that argument, which is frequency n omega naught, and time is tau over 2. Now I'm going to rearrange the terms a bit to uncover some useful properties of this expression. But before we do that, I want to point out that something very interesting happened here. We had a complex valued function that we integrated, and we had a complex expression in the definite integral, but when we simplified it, this here became the sine function, a real valued function. We had as our input an even symmetric function. With an even symmetric function, remember, if I do the trigonometric or the sine cosine form of the Fourier series, I have the b coefficients going to 0. And when I take the complex exponential form of the Fourier series, remember x of n is equal to a of n minus j b of n over 2. This applies when n is not equal to 0. So when the b's are 0, the x's are real coefficients. So this is a pattern that we learn to recognize. If the input signal has even symmetry, then the Fourier series is completely real. And conversely, or similarly, we can say if the signal has purely odd symmetry, then the a coefficients disappear, and the Fourier series coefficients are pure imaginary numbers. In general, they will be complex numbers. Okay, let's go on and rewrite how we are showing this x of n a bit. So here we have our sine term, sine of n omega naught tau over 2. And to uncover some useful properties of this function, what we're going to do is we're going to want to write it as sine over the argument. So the argument is n omega naught tau over 2. So now I have a divide by 2 in the denominator, and it's in the denominator, so it actually comes from this 2 over here. But I have an a over there that I did not use, so I have to keep that a out front. And here I have n omega naught t naught, so my n omega naught got used there, but I still have a t naught, and I snuck a tau into the denominator, so to balance that out, I have to put a tau right here. So the reason we went through this rearrangement is so that we can rewrite the function in this very convenient form. When you have sine of an expression over that expression, that is a special function called the sinc function. And we're going to make use of that notation here. So this is sinc of the argument, which is n omega naught tau over 2. Now, the sinc function, since it is the quotient of two odd functions, when we divide those odd functions, we get a sinc function. It has even symmetry. We can see as magnitude of x gets large, it's going to decay in value because the denominator keeps growing in magnitude, but the numerator has to be bounded between plus and minus 1. The only other important thing we need to talk about now is what happens when x equals 0. Well, then we have division by 0, but it turns out that the numerator is also 0. So if we look at the limit of this function, and one of the ways you could do that is you could take the Taylor series of sine of x, which has no DC offset. It has an intercept of 0, and it has a slope of 1 at the origin. So the first term in the Taylor series is just x, and then there are higher order terms. But if we look at the limit as we approach 0, those higher order terms don't matter, and we can see from the Taylor series, which is providing support for L'Hopital's rule, that the sinc function at 0 is equal to 1 because it's the ratio of sine x over x, and sine x, if we do a series expansion at 0, is going to have x in the term there. So what we end up with for the sinc function is a function that looks like this. It has height 1, and every time the argument goes up to pi or a multiple of pi, so there's 2 pi, there's 3 pi, I have 0 in the numerator. In the case when the argument is 0, x equals 0, we have this special case where it's 0 over 0, and I end up with a value of 1 in the limit. So that is the sinc function. It's going to be very useful for us working with Fourier transforms, and also later we will use it quite a bit in digital signal processing. Now that we have this expression, we can take a look at what the Fourier series looks like. And now here we have, for 3 cases, with a period of t naught is 5 seconds, 10 seconds, and 20 seconds, we are now envisioning what happens with the Fourier series. Let's write the equation here so it's handy for us. X of n is equal to a tau over t naught times the sinc function at n omega naught tau over 2. So now we're showing what happens for a given tau, which in this figure is 1 second long, as we make t0 get longer and longer. Notice as you let t0 increase that the frequency step, the omega naught, gets smaller and smaller and smaller. And therefore, I need n to be higher in order to get up to the same omega. So what we have here is this sinc function, this n omega naught. I could think of that as just being eventually any omega as I let omega get larger and smaller and smaller. Omega naught gets smaller and smaller, so I take smaller steps as I let the period t0 approach toward infinity. This is the general approach that we are going to take to move from the Fourier series for these periodic waveforms into a Fourier transform, which is going to, in the limit, be a continuous function of frequency, because we're going to let this period go out to infinity and take smaller and smaller frequency steps to get longer and longer periods. One thing I want you to notice is for these 3 Fourier series magnitude spectra. They all have identical density. Notice here that the height is getting cut down because I have to divide by the period t naught. But as I'm dividing by the period t naught, I am also including more points in a given frequency range. So if I have a t naught that is 4 times higher, I have also in a given frequency range 4 times as many Fourier series coefficients because they are being put closer together. So I need a higher n to get up to the same frequency. What this means is, and we're going to show this in a limit case, is that the density in any area along this frequency axis is the same for each of these cases. As I have more of them, their height goes down, but those turn out to be in inverse proportion to each other. So if I just add up the heights going across, I have roughly 4 times as many on the bottom as the top, and they are 4 times smaller on average. And at the multiples of 4, they'll actually be exactly 4 times smaller than the original, because all that's changed is t0. If omega naught goes down by a factor of 4 and n goes up by a factor of 4, this is exactly the same, and all I've done is scaled it down by 4, and then I've interpolated at 3 other points in between. So that property is going to carry through as we extend the Fourier series for these periodic signals into the Fourier transform for non-periodic signals. Now we're ready to derive the Fourier transform. Let's go back to the definition of the Fourier series in its complex exponential form, and then we will use the limit argument that we just discussed in order to bring it over to the Fourier transform. So for a periodic signal, x of t, we have known its Fourier series coefficients, x sub n. We can multiply those by e to the j n omega naught t, and we sum those up over all frequencies that are multiples of this omega naught. And in a pair with that, we can build the signal that way, but we can also go in the other direction, and we can say if you have the signal, and we're going to use the variable t prime here, which is going to be convenient for us in a minute, so I'm just changing t to t prime. If we have the signal x of t, to find the Fourier series coefficient at a particular n, you multiply the signal by the complex signal e to the minus j with frequency n omega naught times the time variable. And you do this integral over one period, for example, from negative period t0 over 2 to positive t0 over 2. You do that integral with respect to the time variable, and you divide out the period, and that gives you a particular Fourier series coefficient. Now what we're going to do is we are going to take a limit, and in order to take a limit and change from a sum to an integral, we need to talk about what our differential is. So our differential omega is in the summation, it is the distance between omega as n is going up. So if n goes to n plus 1, I have that frequency, and the frequency next to it is going to be n times omega naught. So that is the step between two adjacent frequencies as I increase n. So we can see that step is just omega naught, and if we put that in terms of the period, f naught would be 1 over t naught, and then to get omega naught we multiply by 2 pi. So rearranging a bit, I can say that the reciprocal of t0 is going to be equal to omega naught over 2 pi, or 1 over 2 pi times the step in omega. And that substitution is going to be useful for us in just a minute. So now I take the original formula for x of t, the periodic signal, and it's going to be a sum over all n frequencies, infinite n. But now for the coefficient x sub n, I am going to substitute in the above formula. So I want x sub n, but I'm going to use this formula right here and substitute it in. And as part of that formula, I have 1 over t naught, which is equal to this expression. So I'm going to write it out this way. I'm going to put my 1 over 2 pi here, and I'm going to put the delta of omega way over there. So that's the step width and frequency that I'm multiplying by to get the 1 over t naught. And now I'm going to continue on with the rest of the expression. So for x of n, I have the integral from negative t naught over 2 to t naught over 2 times the integral of x at this time variable, and times the exponential e to the minus j n omega naught times the time variable. And that, then I have to go back to the expression for x of t, which has this term right here. So I will add that in. And now I will make a couple rearrangements. That 1 over 2 pi factor, that's just a constant multiplier. I will pull that out front. The summation from n is negative to infinity, I am going to change that to an integral. So instead of summing up this expression and then multiplying each by the step in omega, we're going to integrate over all omega. So this is a Riemann sum type approach to transitioning to an integral. So here we have omega goes from negative infinity to infinity, and what we have left inside is this integral from plus or minus half the period. But now remember, we let the period go to infinity, so this becomes negative infinity to infinity over the time variable. And the expression in here is x, which is a function of the time variable. And the other thing that depends on the time variable t prime is e to the minus j. Now we have n omega, which is n omega naught, which is just our frequency now. As we let t naught go to infinity, omega naught became infinitesimally small, and we're multiplying it by integers n going up to infinity. So in the limit, this becomes the continuous variable omega now. And we have our t prime variable still. We also have the second exponential term. That one does not include a t prime, so we have it outside of the inner integral here, so e to the j. Again, we have n omega naught. In the limit, that becomes the continuous variable omega times t. So this expression here shows the Fourier transform and inverse Fourier transform together. So what we have here is we have the inverse Fourier transform of the Fourier transform of the original signal x. So if we break that out into two parts, the Fourier transform is the inner part, so we write that as capital X as a function of omega now, instead of n, which told us what frequency number we were at. We now have a continuous frequency, so we specify omega. Symbolically, we often use a script f to indicate a Fourier transform, and above we wrote it as x of t prime, but the name of the time variable is arbitrary, so I'll just call it t here. And that is the inner integral. The inner integral from negative infinity to infinity over time, so this is inside the square brackets, of x of t e to the minus j omega t. So this bears some resemblance to the Laplace transform in form, but we have j omega instead of s in the exponent is the key difference. And then the inverse transform is the outer part of the equation above, so we can recover the signal x of t from its Fourier transform function x of omega. And the symbol for that, this is the inverse Fourier transform, so script f inverse applied to the Fourier transform x of omega, and that is the outer part, so it's 1 over 2 pi, the integral negative infinity to infinity, and the inner part we called that x of omega, so I'll use that symbol here, and e to the plus j omega t d omega. So here we have a way to analyze a signal, take x of t, and do this integral, and now it becomes a function of frequency instead of a function of time. So that's the Fourier transform, or the forward Fourier transform. Once we have this function x of omega, which tells us about frequency content of the signal, and it will be complex valued in general, then we can go back to the original signal by doing this integral, which looks very similar, except it's plus j omega t here instead of minus j omega t. Remember this original minus j omega t, that came from the time reversal in the convolution formula when we derived frequency response at the end of chapter 2. That's why in signal processing, where we deal with convolution, we define the Fourier transform to have a negative j, not a positive j, in the exponent. Some other branches of mathematics and sciences may differ on having a negative exponent here versus here. They have to be conjugates of each other, but we have it here for that reason. And other branches of science also sometimes differ on how the 2 pi factor is apportioned between the forward and the inverse transform. But here we are using the standard signal processing definition used by engineers. So we have a way, given that function, x of omega, to do this integral, scale it by 2 pi, which came out of the relation here of angular frequency to frequency in hertz. That's where the 2 pi came from. We have a way to do this integral and get back to our time domain signal. So now we have a way for signals that are not periodic to look at what content do they have as a function of frequency. And sometimes that will be a simpler view, and so we might prefer to analyze the signal here on the transform side, and we're going to do several examples of that later in this class. And then eventually we need to know what the time domain signal is, so we do have a way to do the inverse transform and get back. Let's do one quick example with the rectangular pulse and see where we got in the limit. So the rectangular pulse, now this one's no longer periodic, it is just a rectangular pulse from plus or minus tau over 2 with height a. This is our x of t. And now let's do the Fourier transform of this. X of a function of omega is the integral over all time, but it only has non-zero values from negative tau over 2 to tau over 2 of the value of the function, which is just a, the amplitude, times e to the minus j omega t dt. And we do that integral, so we get a over minus j omega and the a to the minus j omega t where the value t is going from negative tau over 2 to tau over 2. This looks similar to what we did at the start of this section. We're going to end up with the sinc function. So let's work it through. So I have e to the minus j omega tau over 2 minus e to the minus j times omega times minus tau over 2. So it'll be e to the plus j omega tau over 2. And now I need to simplify this. So inside the brackets, I have a vector that is between the points e to the plus j omega tau over 2. And I'm showing here that omega tau over 2, it looks like it's about 50 degrees, but it could be any angle. I'm just showing an arbitrary value here. And then the conjugate is going to be right there, e to the negative of that, e to the negative j omega tau over 2. And here in the expression, I can see I have the vector. If I look at this in vector form, with its real and imaginary parts being my horizontal and vertical vector components, I am going from the plus 1 to the negative exponent. So I'm taking the vector from here to here. So that expression in brackets is going to be in the negative j direction, and is the sine, which is this value right there, that is the sine of the angle, and there's two of them, and it's in the negative j direction. So I have a over negative j omega, and in the brackets I have negative 2j sine of omega tau over 2. So negative j cancels out, and I end up with 2a sine of omega tau over 2. And now I'm going to rearrange a bit again to get the sinc function. Oh, I have a omega there. Okay, omega in the denominator that I forgot to carry over. So now we want to build this in terms of the sinc function. So I put my sine term here. And I want the argument of the sine to be in the denominator. So I have omega tau over 2 in the denominator. The denominator divided by 2 takes care of this 2 here. The denominator with a omega takes care of this omega here. And I also have a tau in the denominator, so I need to balance that out with a tau in the numerator. And I have my original a, and I've taken care of all the terms of the denominator out front, so I just have that. So I have a tau sinc omega tau over 2. So let's sketch that resulting function. So here we have the sinc function as a function of omega. The sinc function has a peak at 0, and then it oscillates, but it is divided by a growing denominator. So the magnitude keeps scaling down. The sinc function at omega equals 0 has a value of 1, but we've scaled it up at the peak here, so the peak is at a tau, and here we are plotting x of omega. Now, in general, x of omega is a complex number, so we could plot its magnitude in phase. But for this particular case, since we have a non-periodic signal with even symmetry, it turned out to be a real function. So I'm just plotting x of omega here. It goes positive and negative. So, if we plotted the more common magnitude of x of omega, then I would have these negative lobes. I would just rectify them and have take the positive value. But here I'm showing the actual x of omega. And now the sinc function, it crosses through 0 every time sine of its argument is 0. So every time omega is a multiple of pi. So I'm tempted to label these 0 crossings as pi, 2 pi, 3 pi, and so on. But note that we have a scaling factor of 2 over tau. We've sped up time by tau over 2, so I have to multiply by 2 over tau each of these frequencies. So the 2 pi gets multiplied by 2 over tau, and I get 4 pi over tau. This third 0 crossing would be at 3 pi, but I multiply it by 2 over tau, and it's at 6 pi over tau. And so those 0 crossings repeat every 2 pi over tau. Finally, let's talk about convergence of the Fourier integral. Fourier transform integral. So this is a somewhat complicated subject, but let's talk about a few cases. If the function x of t is absolutely integrable, this is a sufficient condition for the Fourier integral to exist. So I can take the Fourier transform for any signal that meets that condition on the left. It is not a necessary condition. We will see later in the chapter there are examples of useful signals such as x of t equals u of t. That is not absolutely integrable. When I go to infinity, the area still goes to infinity. So that is not absolutely integrable, but we will show that the Fourier integral exists, and I can take the Fourier transform. So we're going to have a few different techniques that we use. One technique is a limit case. So if we have x estimates a function and it has some parameter, epsilon, and if that function is well defined and we can take the Fourier transform for epsilon is greater than 0, then we end up taking the limit of the Fourier transform as the epsilon goes to 0, and it will converge. So that is one technique that we will use. There are some others that we will use later in the chapter. So generally, well-behaved functions that are bounded will generally have a Fourier transform that exists. There are some exceptions, and for some of the signals, like the ones that are not absolutely integrable, we will need to use some alternate techniques, but their Fourier transforms do exist. The key point here is the Fourier transform is an extremely versatile tool to handle a wide variety of non-periodic signals that we as engineers want to work with. It will also, as we show later in the chapter, we could even use it on a periodic signal, and we'll see what happens. So it is a very powerful tool. There are many different types of signals that will yield to Fourier analysis, and not merely the ones that are absolutely integrable.